Good afternoon, everyone. Welcome to another session of Network Capacities hosted by the Center for Network Intelligence and the ECE and RCCPS IIC. Today's talk is by Professor Aurélien, and we will be speaking on missing mass and optimal discovery. Professor Garivier is a professor at Ecole Lyon in France. He works in the realm of stochastic and statistical modeling, approaching the subject from diverse perspectives. With a PhD in information theory, his research has primarily focused on machine learning, with a particular emphasis on reinforcement learning. Professor Garivier's most influential contributions pertain to the field of matrix models. His research interests extend beyond this domain and encompass Markov models, perfect simulation, and the optimization of stochastic functions, among others. Notably, he has recently delved in the areas of differential privacy and discovered reinforcement learning. We request the online audience to please keep your microphones on silent during the duration of the talk, and you can unmute yourself for any questions. Over to you, guys.
Thank you very much for the very kind invitation, very nice presentation. I'm very glad to be here, and so as you said, please interrupt me whenever you have questions, because it will make the talk more lively, and you don't need to keep your questions for the end. Actually, I will tell you about a work that I did a few years ago now with Sébastien Dubek, who you may know, who works at Microsoft in Seattle, and Damien Ernst, who is a Belgian researcher in electrical engineering, and who came with the problem that I will explain you in a few moments. But before that, we will make a small statistical parenthesis about a nice problem. Pretty surprising. I don't know if you don't know about it, in fact, an estimator for estimating what we don't see. So estimating the unseen, I will explain that. Then I will come to the actual problem we will be interested in during this talk, and what solution we propose and analyze with Sébastien on this particular problem from two perspectives. The first one is rather classical, is the minimization of regret point of view. The other one is a bit more specific to that problem, and we will see that it gives a better insight into what happens in that case. So first, estimating the unseen. Actually, it's an old problem. You may have heard about the Enigma machine during World War II. There's a very nice book, if you haven't, by Simon Singh, about coding, deciphering in general, the code book is called. And it's a wide audience book, so it's written for non-specialists, but it tells really a lot of things of the history of ciphers, deciphering, and things like this. And there's a nice chapter about World War II in particular. And during World War II, the Germans were using a machine for all their communication that was called Enigma, and that was really powerful and hard to decipher. But it took some mathematicians a lot of effort to indeed manage to do it. Actually, the first mathematician was Polish, and in the 30s already he had the first positive result from the deciphering Enigma, but then the very famous name worked on it during World War II was Alan Turing, and which is a very famous story. I strongly encourage you to read in this book. Actually, the machine was like this. You had a keyboard when you wanted to write a T. Actually, you didn't transmit the T. You transmitted the letters that which lamp would light up when you touched it. So you press the T corresponds to a K. It goes through three wheels that are turning at different rates, and then it comes back to all this, and so it illuminates some letter that changes, of course, at every time you press it. And the system is pretty, even if you know it, it's really difficult if you don't know the settings here to uncipher the code. And in order to do this, the system was really had a very huge combinatorics. It's really strong, except for one thing that Alan Turing and Irving Good had remarked, is that actually you need to set the initial position of the wheels, and they did some setting every day, the Germans, and in order to set it, they would use a 3-letter code, and to choose that code, they would pick a book open a random page and take the first letters of that page. And that would give them the setting for the rotors for the day. And so the weakness was that if you do this, you don't have a uniform probability of choosing 3 symbols among all the possibilities. Because the book, you don't open it at the first page or at the last page, you open it more or less in the middle, and so the letters were not uniformly sampled. So you wanted to estimate in a way the law with which the Germans were opening their book and picking those three letters. It's a huge alphabet, of course, and you have only a few observations. Far fewer observations than you have possibilities, and still you want to estimate the probability of the combination you have already seen, and also the probability of seeing a new combination you have never seen before. And how do you do that? How would you estimate something you didn't see so far? So this is a problem in a more formal presentation. You have a discrete alphabet A, it's an unknown probability distribution on it P. You have independent samples from P, x1, xn, and the goal is simply to estimate P of A for all A in the alphabet. Seems to be the most simple problem in the world. The first one you learn in statistics, and you will tell me, or the answer, the best answer in many statistics is, well, empirical average, maximum likelihood estimator, the number of observations of A divided by A. Okay? Well, it's not a good idea. In my context, it's not a good idea. So let's take another context where it's not a good idea. So you go to the savannah and you want to estimate the proportion of each animal among the living beings of the savannah. And so in your first day, you see 1 giraffe, 2 elephants, 3 zebras. And so should you really estimate that 1/6 of the animals of the savannah are giraffes, 2/6 are elephants, and 3/6 are zebras? So if you do, you might go into problems the next day. So it's not a good idea. How do you estimate what you haven't seen so far? Another context where this is really important is the context of linguistics, the classical pre-deep learning methods, where trying to estimate directly probabilities of occurrence of words, of sequences, so by some kind of a Markov model, and so you wanted to estimate the probability of a sequence by the product of the conditional probabilities of seeing a symbol after another. And it's another context where you have many possible words in particular. And so you can't hope, even with a big textbook, to estimate those probabilities correctly by maximum likelihood. You won't have sufficiently many occurrences of the word Moby to estimate what is maybe not the best example. Take it to the words here. To estimate what is the law of the next symbol after that. There's always a pretty high probability that you see a new word after some given word that you haven't seen in your corpus where you learned, obviously. The unseen must be treated correctly in that case. So how to estimate this? Well, the most simple idea would maybe go to Bayesian statistics, because that's what they allow for. So, for example, yes, that was Pierre-Simon de Laplace example in the 19th century, telling you what is the probability that the sun will rise tomorrow. So it's a number of observations plus the number of observations divided by the number of observations plus or something like this. So it gives some small room for the possibility that you haven't seen so far. But why? It's pretty arbitrary the way you correct for this. I mean, and it underestimates, well, yes, it's arbitrary. It's not satisfying. And as we will see, it can underestimate massively the probability of things you haven't seen so far. When the alphabet is very large in particular. And when it is infinite, it makes no sense at all. So this is not a solution for the problem. Actually, a pretty good solution for the problem was proposed by Alan Turing and Irving Good. So you will see there was a bar here, who were working at Bletchley Park on the project of the Good-Turing enigma for the application I showed at first. Maybe stop a little the flow of my speech. a quick question: how many of you know about the estimator they proposed for the answer, which is called the Good-Turing estimator? Who has already heard about the Good-Turing estimator? Okay. So yes, it's pretty known in information theory, where people want to address very large alphabets. So for universal coding, for example, on large alphabets, those are ideas that have been studied quite a lot, even on the recent years. The idea would be to use a few things that appear not very often in the sample. So we will call O(n) of x the number of occurrences of the symbol x in the sample of size n. Okay, so O(n) of x, number of times I saw in my sample. And the question, we will phrase it, is to estimate the mass of the unseen, that is to say, the sum of the probabilities of all the events that I haven't seen in my sample. Okay, so it's not, strictly speaking, an estimation problem. It's not a parameter what I want to estimate. It's random. It depends on what happened so far. But still, I will have to have an idea of what is the total mass of what I haven't seen. Or to put it differently, what is the probability that the next symbol I will observe is not in my sample so far? So how do I estimate it? At first, it may seem really an impossible challenge. But the idea is to use to estimate the mass of the unseen by using the hapaxing. So in linguistics, it's a linguistic word. An hapax, the corpus, is a word that appears only once. So here it will be an item that appears only once. We call UN the number of items in our sample that were seen only one time. Okay? And the idea is to estimate the mass of the unseen by the proportion of hapax. That is by UN divided by n. Surprising at first. Not so surprising. So there's a very simple lemma I leave you as an exercise. I'm sure you can do it, which shows that in expectation it's very good. And this was a result published very early in the 50s. It's actually credited by Good to Turing during World War II, but of course they didn't publish at that time. And so you find that on average, it's still a good idea. You have a very small bias between the two concepts. So why does it come? The proof is here. As I said, I won't go through it. You just see that it's a sequence of simple equalities. I'm sure you can do it. Actually, there's a natural explanation of how you come to consider this example. It's just out of the box or the jackknife estimate. Okay, so if you had one additional sample, you would estimate Rn just by the probability. You do as if, say, x1 was not in the sample and the rest was your sample, and you would see, in that case, by one, you would estimate the probability to see something unseen. So you would put a 1 if x1 is not in the rest of the sample, and a 0 otherwise. That is to say, you would exactly add a 1 if x1 appears exactly once in your total sample, it's not in the rest of the two. So this estimator R bar n is exactly the jackknife estimator. So it's not so unintuitive as may first seem. So the question is, okay, this estimator is good on average, but is it good? Is there a good concentration? Actually, that is, say, is R hat sub n close to its expectation, and is Rn close to its expectation? It took at least 40, 50 more years to obtain satisfying results on this. But one can see it. Actually, the bounds we kind of used was this one. So one can prove not only that the expectation they are close, but also that they are both close with high probability. so that Rn is close from R hat sub n at a distance that is log 1 over delta divided by n. That is the standard Gaussian deviation concentration that you can, the best probably you can hope for such algorithm. So how do you get such a result? Well, you have to concentrate separately Rn and R hat sub n. It's not the same problem. For R hat sub n, you have a simple way to concentrate it. It's just that if you change one value of your sample, at most you change the number of abaxes by 2. Okay? You had an abax, you remove it, and you add it to somewhere which was an abax, you lose 2 abaxes by that. So the impact of one change in the sample over the estimator is limited to 2 over n. So you can use McDiarmid's concentration inequality to have sub-Gaussian concentration for R hat sub n. This is not at all true for Rn, because you want a bound that is completely independent of the distribution P. And in P, you might have only elements with a very tiny probability, or you might have one element with a probability 1/2. So you cannot say that the impact of changing the sample by only 1 point will have an impact on Rn that is only 1 divided by n. It's not lower one, it can be 1/2. So you don't have this McDiarmid argument problem. You need to work more, and actually it's very beautiful. There's a remarkable paper by McAllister and Shapir, and later by McAllister and Ortiz, where they use negative association to prove those kind of results. Plus, a lot of smart ideas on Chernoff transform and the statistical physics view of the Gibbs distribution you obtain. It's a very beautiful paper you may look at. Another technique for this is Quest mutation, where you get some independence, and that is used in some other papers. Okay, so now we have we have an estimator for the missing map. So why did I tell you about this? Actually, it all comes to a problem that was posed to us by Damien Ernst, who works on electrical systems, and specifically, he works on trying to find complicated configurations in electrical systems. So he works in Belgium, but they have a figure for the US. So imagine you have a complex network of electrical network, and each node can be in a given state. So the number of possible configurations, maybe a 10 to the 18 or 10 to the 20, it's huge. And you want to find among those configurations those that pose a certain problem. Some interesting items. The problem is there are plenty few of them. And obviously, if you try to estimate by Monte Carlo, if you sample at random among the set of all possible configurations, you won't find any, ever. The space is too large, and you can't find them like this. So how to quickly identify contingencies that would lead to unacceptable operating conditions to prevent, if not preventive actions for thinking. So fortunately, there are engineers. The engineers, they provide some intuitions on configurations that will probably lead to difficulty. So they allow you to sample from the set of possible configurations, but not at random. Each expert has intuitions, and so each expert corresponds to one probability distribution on that set. And the problem that Damien posed us is, how do I use my probabilistic experts, my different ways of sampling, so as to find a maximal number of interesting items, dangerous configurations, as soon as possible. So in a way, he said it's a bandit problem, because it's like in a bandit you see case where you have several arms. Here the arms are the distributions, and you have some reward, and the reward is one when you get a new interesting configuration. But obviously, it shares some common elements with one problem, but it's not a main problem. Because, well, once you have found an interesting configuration, it's no use at all to find it again and again and again. So imagine you have a perfect expert which is actually not random. It always samples one configuration that is indeed interesting, well, you use it once, and after that you can throw it away. You don't need to. It's no use to use it again. So it's not a bandit problem in that sense. A bandit algorithm on this data would lead to very, very poor results by overusing some limited potential experts. So maybe this is expert 1, maybe this is expert 2, expert 3, and the goal for you is to combine, to use all of them, but in an optimal way, so as to find as quickly as possible as many interesting items as we can. Let's see the formalism for this problem. So you have a discrete time, 1, 2, 3, 4. At each time you pick one distribution, so IT is the number of distribution you will use. You choose it obviously according to your past observations, as usual in bandits or in sequential statistics. And then you observe a new draw from this random distribution. Okay? And your goal is to design a strategy, the way of figuring here, so as to maximize the number of important items found after T requests. So I notify F phi of T, so found with strategy phi at time T, the number of interesting items you found, that is the intersection between A is the set of the subset of important items with the samples you have obtained. Okay? So this is what we want to do. We want to maximize the F phi of so far we made for simplicity, we made the following assumption so far: that two experts will not give you the same configurations. So the intersections of the support of two experts with the interesting items is empty. So as I said, it looks like a bad problem because you have sequential choice from k options. You want to maximize the cumulative reward. You have an exploration versus exploitation dilemma as usual. But it's really not a bad problem. The rewards are not IID, as I said before, and they are destructive. Once you have observed something, you don't want to observe it again. No use at all. And moreover, you can figure out that in the end, ultimately, after a lot of time, all strategies are equivalent. If you may draw as many samples as you want, in the end, you will have found all what the expert could give you. So, how do you do?
Can you go back to the condition you had?
Yes.
So, can you explain the support of PI?
Yeah, so it just means that the support is all the elements that have a positive probability under PI. Okay? So, the PI and PJ must not give positive probability to the same interesting item. They must provide you different interesting items. Okay, it's not that restrictive. In fact, it can be relaxed if the support of the intersection.
For example, suppose of PI for every I, suppose it's the entire set. You can get any sample.
Yeah, in that case,
that will not be.
Yeah, that will not be. Here you see in my example, they sample from different places. So in a way, they could sample jointly, but not the red. And as I said, you can relax this assumption, but with another assumption telling you that the probability of the intersection is small with respect to the probability of each.
So in some sense, this is saying that you should force yourself to sample from I, from J, from
yeah, not one expert will give you all the thing is probably maybe I gives you 100 interesting configurations and J only gives you 3, but you don't know at first. So in the end, you will use 2 of them. But probably at the beginning, you should really use I for a long time until you get 97 items, and then only you use the second one because there are only 3 to find this one and 3 to find this other. So okay, this is the challenge between exploration and exploitation in that context.
Sort of forcing you to explore.
Yeah. In a way, at some point, there's a strategy that in the end finds everyone, the uniform sampling strategy. If you sample the experts in a round robin way, you will, in the end, find all the items. So in the long run, all strategies are equivalent. The problem is to be better than this. At some fixed time to have found more items that's uniform ordering. Okay. So it's pretty clear from an intuitive point of view, but the proposition you can prove that the optimal strategies, what does it do? So at every time step, it samples from the distribution that gives you the highest probability to obtain an interesting item, not seen before. Okay, so at each time step, what you should do is pick the expert that has the highest probability to give you an item that's interesting and that you haven't seen so far. So it's exactly a problem of the missing math estimation. What you want to know is what is the math of all the interesting items you haven't seen so far using an expert. And so the question is, well, once you realize this, you can have an idea. First, once you realize it, this gives you an oracle strategy. The oracle strategy will do this all the time. It's cheating because you don't see, of course, the probability of the items you haven't seen. But still, it's the optimal strategy. No strategy can be better than this, whatever happens. And so for every possible strategy, the expectation of the number of items found by P is smaller than the expectation of the items found by this base strategy, oracle. But if you have some bandit culture with yourself, you can say, okay, in that case, I can do something like UCB. I will estimate my meeting math, and I will not use the estimate because I know in bandit setting it's not good. I will use another bound of the estimate. Instead, I will use the good UCB algorithm. Good UCB, that's how we named it. Good for the Good-Turing estimator, and UCB for UCB. So it's a paper with particular Sébastien, Damien. And we will see what we said. So first, what is the estimator? So it's pretty straightforward. Here, I estimate the missing math by the number of half active, just as before. So it's the Good-Turing estimator for each of the arms separately. And what do I do? Well, at each step, I pick the arm that has the highest index, the index being missing math estimator plus the confidence bonus. Bonus, as usual, is some constant square root of log t divided by the number of observations. Not surprising at all. So then I do the observations and I update my indices. And I continue like this forever. So is it a good strategy? Well, actually, this is not the first result we obtain, but one can mimic a classical bandit proof, bandit regret analysis, like the one of UCB, for that context. And if you do, you will obtain a regress bound that is very reminiscent of what you have with UCB. The difference between the optimal oracle strategy and U will be upper bounded by square root times k number of arms and t log t plus some random terms. It's not straightforward at all. I won't go into the detail of the proof. It's a bit technical. It's not. Well, you have a few things to realize to obtain. Yeah. Despite the fact that you obtain a result that is pretty expected. So there is a sketch of the proof here. It kind of looks like usual, but there are some differences. So first, you would say that you focus on the subset of the probability space for which the confidence intervals are true all the time, and then you say that on that set, the true missing mass is not very far from your estimated missing mass, and then you have to compare. The problem is that what you have done so far is not the same as what the oracle has done so far, because he has followed the optimal decision at each step, and you haven't. And in order to make that proof, you have to show at some moment that actually your opportunities at every time t are better than the opportunities of the expert at every time t, which is pretty normal. The expert is greedy, he's taking all the best options to observe some interesting items. So after some steps, he has less opportunities than me. This is a bit not so easy to write. That's kind of the difficult part. The easy part is to conclude then by summing the difference between what the system regrets as quite usual in publicity analysis. But let's look at what happens if you do an experiment. So in this is just a sample case where we have 5 experts and we have them running for a certain time. So in red, you have the uniform sampling strategy, which shows you how many interesting items were found over time, and you see it's an increasing function, obviously. In green, you have the cheating strategy, so the oracle strategy, the one that knows what we can't know. And in blue, you have our strategy, which is the good usage strategy. So it's satisfying in the sense that, okay, you are indeed beating uniform sampling by far, and you are not very far from the optimal strategy. What is not satisfying here is that you don't at all observe regrets growing like square root. Maybe at the beginning a little, but very soon not at all. This analysis doesn't reflect what happens in that case. And so we had to think about another analysis that would, in particular, take into account the fact that after a lot of time, all the strategies are equivalent, as I already said. You have everyone, a stupid strategy will find all the items. So, how to come with a result that reflects this reality? So, to do it, well, we changed the point of view in a way, and we took the dual problem where we fix a certain fraction lambda, and we look at the time t of lambda, at which the missing mass of important. Let me move my. The missing mass of important items is smaller than lambda on all the experts. Okay, so it will take you some time. This random time t of lambda, and our analysis amounts to showing that actually this t of lambda is not much larger than t star of lambda. It's not really t star of lambda. It's the time the optimal strategy, the cheating oracle strategy, would need to reach not exactly the same lambda, but a slightly smaller lambda. And the time you need is a bit larger than the time the oracle needs to reach a level a bit lower. That's the general and more satisfying result that we have, that will have good implications. So, for example, what happens when the size of the bag goes to? This is the analysis we prefer, the one with the limit, speed limit, when you normalize things in the way we do it here. So the way we did it here is we have 4 experts. So this time their intersection is really empty. They have a fixed proportion of interesting items, but the size of the bag grows in our limit with a parameter that is called n. And the question is, what happens when n goes to infinity? And in that case, our result is to study this limit and to say that our algorithm in that case, first, the oracle strategy. In that case, the oracle strategy, for the oracle strategy, t star of lambda, correctly normalized, is not random. What will happen in the limit is not random, it becomes deterministic. The time you need to reach a certain level, the size of the bag goes to infinity, becomes deterministic. And the oracle, it actually there is a special form for the oracle. You can solve it in that case explicitly. And what you obtain is you can even bound the proportion of items found after empty draws by the oracle and by the uniform strategy. And you can look at the ratio to measure the efficiency of the optimal strategy with respect to uniform sampling, and find that it is exactly the ratio of mean, average, to a geometric. So it's always larger than 1. So you can quantify easily exactly by how much you improve the speed of finding items with the optimal strategy. And you improve all the more when the QIs, the proportions are unbalanced. Because if they are balanced, the uniform sampling is optimal. But what is interesting is that we could show that the OR strategy, indeed, in that case, reaches the limit of the oracle. That is to say, it will also have a behavior when the size of the bag goes to infinity that is not random, and that is the one of the oracle. So the proportion of items found after empty steps by our strategy converges uniformly to that of the oracle strategy. And let's show this in a few plots. So this is an experiment. Same proportions in each case, but this is the plot I showed you before. This with a small bag. Same experiment with the larger bag, and what you see is that indeed the curves for the optimal strategy and for the uniform sampling tend to be deterministic, and you have a uniform convergence of the curve of discovery of the Good-Turing strategy to that of the oracle. So this reflects in a way much more what happens in reality and what quantifies the edge, the advantage of our strategy over uniform sampling. Okay. In that sense, it's a kind of non-standard analysis for bounding problems, which are rarely seen in such a kind of asymptotic. Okay, so the last point is what do you do if the assumptions are not satisfied? So this is what you suggested. We took a stupid example. So we wanted to know how many prime numbers would be found by good UCP, the Ecole, or uniform sampling. And the experts we took were geometric distributions with different parameters. And so they have the same support. The support intersected with the prime number is not empty. But still, what we could observe is a kind of same phenomenon, in fact, empirically, that we do much better than uniform sampling, and we tend to be optimal. Okay, so this is it, more or less. I will quickly wrap up. So we have proposed an algorithm for optimal discovery with probabilistic expert advice. It's not a problem that we pose ourselves, it's actually a true application that motivated this model, and which we found pretty funny. So we provided a standard regress analysis for this under mild assumption, but we were not really happy with this. So we studied a specific optimality result in that case with a different view that permits a macroscopic analysis in the uniform case. So yes, I didn't say that this we did only in the uniform case, but the figures are uniform all the time. And another interesting limit to consider is the number of FII. We could have done something else here when we took the limit. Here, what we kept constant over time is the proportion of interesting items. What we could have kept constant is the number of interesting items. And in that case, we would have probabilities going to 0, and there would be other scalings, so we need more and more rows. But that would also make an interesting limit. That limit would be random, not be deterministic in that case. But it's also maybe interesting to see. It's really a Poisson regime. Of course, in the Poisson regime, our algorithm would not be very good. And in order to improve it, we will either need better deviation bounds, not you see, we would need to go set a metaphor from everything to Bernstein inequality. We would need something including the variance. But yes, this remains completely to be done. And so I thank you for your attention.
What was, so the algorithm did not change, only the analysis changed.
Yeah.
To be able to demonstrate that it's actually that all algorithms are eventually equal. So the rate eventually is going down. What was the failure of the original algorithm? Why did it fail?
So the algorithm did not change. The assumptions changed because here in that case we are using that the experts are uniform to it. It may be possible with a lot harder. What fails in this analysis is in the classical analysis is this step. Okay, here when you bound the regret by a sum of instant regret, what it fails to catch is the fact that if you were very bad at the beginning, you have more opportunities and you will catch up. And this catch-up phenomenon is not at all counted by, taken into account, reflected by the regret analysis where you accumulate errors in a way. Okay? At each step, the standard analysis says you're not too far from doing the best decision. The problem is your best decision is a lot better than the oracle's best decision if you perform poorly so far. So this is not caught by the user. Yes, we know how to improve. I don't even know what the result would look like. More or less, those bounds, like well, the regret is bounded by square root t, are kind of structurally additive. I don't know how to add negative terms here. That should appear. Is there any question from online audience as well?
Is there any question in the chat? No question.
Yes, perhaps one question which is more related to the application side.
Yes.
Have you seen other applications and because you can imagine that you have maximums that are some kind of events that are wrapped in your set, in the combinatorial space, but you have access to experts that are quite good and can help you finding it. Will you try to rephrase it this way?
So if I understand correctly, what you suggest saying that using classical bandit algorithms can be used to for in machine learning for tuning the parameters.
It's a good example.
Yeah. And here, what you say, if you want to maximize things or to do some maximization, this could also be the case. Actually, maybe, yeah, maybe it's interesting.
I imagine that the sets of possibility have the same properties, right? Like the goods point as kind of green sparks among all your solutions. The only thing that I'm not able to wrap up is this kind of expert thing which is able to sample.
Yeah,
so
exactly.
This is where I'm stuck.
Yeah, so you would need a stochastic approximation scheme that will do its job with a certain probability, but difficult to control.
Yeah.
But that would not be probability one. Why not? I mean, it could be, yes. I haven't really thought about so far,
but in which situation, otherwise, you have this kind of expert sets?
Yeah, optimal discovery thing I don't really know about. Yeah, so I didn't work so much on the application side. Daniel, when we gave the application side for this paper, we were more on the algorithm and theory for it. But yeah, it's probably worth. Like when we did this part, we thought, oh, this must be a problem that comes pretty often. In fact, yes, you want to find things, you have several ways, you don't know. But so far, I must say, this is not one of my most cited papers. So I don't know if the impact was really huge. But yeah, still, I think that it's a nice idea. At least we'll have learned about the Good-Turing estimator, and only for that, we did well to the later.
And related to all this integer choosing the right answer and things like that. So the only difference is really the kind of experts that you are working with, right? In Bandit, you can sample it multiple times and so on. And in this case, you know that basically they just sample well one time, and that's right.
They can sample well a few times, just destructive. You are kind of exhausting them. When you are using them, they get less than they expect. Yeah.
We can think of an application.
Students.
Exactly. So
I will
be careful where you go.
Okay. To understand the estimator itself that you see the estimator.
Yeah.
So you can just help me pass that. So the first one is looking at how often up to time t-1 have you seen, how many elements have you seen exactly once, right? That's the
Yes, exactly.
how many elements have you seen exactly once. But not only that, that element should be
And that they shouldn't have been seen by the other experts. So there is a J.
now you wouldn't have needed that in your assumption.
No, in my assumption, this is impossible. But as I give the estimator as the algorithm, even if that assumption is not satisfied. This is how we use it in the case with the prime number finding when it was not. So you're totally right that if we are in the context of the assumptions that I wrote before, yes, here that doesn't happen. Yeah, exactly. But for the general algorithm, it's right.
The algorithm had the T where you're looking for extraction less than lambda.
Yeah.
You had a bound on that based on the T star.
Yeah.
Of course, T star is not dependent on the lambda, but on the things called the lambda. I'm trying to understand. This is the non-fluid limit result.
Yeah.
Something that. But where did this come from? The fluid limit suggests this idea, or in other words, what was the purpose of the fluid limit in the analysis?
Yeah. So you're totally right that this bound is totally independent of anything, and it's true in general. And this is why it is given before I present the limits we are taking and before we assume uniformity that just the idea of considering this was really the experiment and this kind of experiment. And the fact that the catch-up phenomenon, we couldn't reflect it in the classical analysis. And we thought it was a crucial feature of this. And it was really very hard when you fix a vertical line like this to express this catch-up phenomenon. While when you draw an horizontal line like this and you wonder what is the time you need to reach this horizontal line, it's more easy. And these horizontal lines correspond to this star of T of lambda I. What your algorithm is doing, by the way, is trying to make uniform the probability of finding interesting items among the different arms. So when one has a higher probability to be drawn, you use it until it gets less interesting and it reaches the second one, and so on. So when you understand that, it's pretty natural to consider this quantity time you need until the probability of interesting items under each expert is lower than some level. Because yes, this is what your algorithm is trying to lower. Even what your oracle strategy is trying to drop up to 0.
somehow there is also an association of interesting events, thinking of the application, of the interesting events that you see, which is the set A.
Yeah.
With the number of events that you see exactly one. So if you can go back to the estimator once again.
Yeah.
So somehow you should know that this is an interesting, these are all interesting events. X in A. That is, when you see an X, you should know that it is A or
That was exactly Damien's assumption. So you're telling me, you give me a configuration, I have a simulator in 1/10 of a second, I can check if it is dangerous or not. If you give me a simulation, a configuration, I check if it is interesting or not, that's the cost claim. The differential point is that I have too many configurations. You're right, I should have more on this. So you have a, when you see a point, you see, you know if it's interesting or not. That's right.
if you do not know, then I think it probably leads to a
if you do not know it, you need some way of feedback, otherwise if you have no information at all, what can you need a way to know or to estimate it. It could be noisy, but it change a lot. The probability that it's dangerous would work as well, but in this case, just test and you know.
if you can design the P itself now, I mean, in the sense that right now you're relying on an expert, you're saying, okay, this expert, sample according to that. But actually, in some sense, the set of P's that you have accessible to you, not just those arms or those experts, you could design the P yourself.
The P yourself. So it depends what you know. If you can cheat and you know what are the interesting items, but I guess the optimal experts will of course be concentrated on the interesting items and only on that. You can have either one expert only interesting items, or you can share the interesting. So in a way,
but there's no optimal expert yet because an expert only focuses on subset under that.
But overall, this makes the process of discovery very, very quick. But so that's too much of cheating, and did not correspond to Damien's suggestion. But I understand. So if you can build,
I'm looking at the power system.
I
can mix the experts.
but how do you mix them?
That's what I'm asking.
Okay. So if all you're allowed to draw is to take linear combinations, say or mixtures of the experts, that's more or less what we do. I don't think it's different. And it's interesting. I've never thought about it. With the possibility to mix the experts, so that would be cheating. You could mix them. So imagine you know your expert and you know their initial performance, and now you're allowed either to draw the experts or to draw a mixture of them. So in a way, yes, it's included in the initial model. It's just a two-step.
The assumption holds, then it's probably just same. What you're sampling is probably the same.
Exactly.
But you find out.
Yes, you're right. Okay, if there are no other questions, thank you very much again for your attention.
We have arranged for the questions at the copy. Please help us.